So let me start my session. Just confirm uh, whether I'm whether the screen is visible or not. Am I audible or not? One of you confirm, please.
Audible, sir.
Fantastic.
Yes, sir. You're audible.
Great, great, great. So we are learning our subject data engineering, and we have completed Unit 1. We have completed Unit 2, and in Unit 3 we have completed Hadoop distributed file system, as well as we have completed data generation till here. So what will be our today's target? Today's target will be a topic called as storage. Okay, so which involves raw ingredients, data storage systems, cache and memory based storage. Then we'll be looking at storage abstractions, big ideas and trends in storage. As I repeatedly tell you in the class, this book has a lot of discussion. So there is always scope for compressing that discussion and focusing on the key points. So my today's session will also be on the similar lines, though I'll be giving a walkthrough of the chapter of the prescribed book. Which prescribed book I am speaking about? This prescribed book, Fundamentals of Data Engineering by Joe Rees and Matt Housley. So this book, though I'll be referring, as I said, it will be a compressed version. It will be a compressed version. Give me a minute. Let me start this. This is our prescribed textbook actually, and from this prescribed textbook we are going to discuss the topics which I'll repeat again. What topics we are going to focus today? Raw ingredients of data storage systems, cache and memory based storage, storage abstractions, big ideas and trends in storage, and that too very in a precise, compressed, shorter version manner. This is our chapter storage. Let me highlight that storage word from the syllabus. And in storage, the first line is raw ingredients of data storage. Okay. So we all know the significance of storage in data engineering life cycle diagram. We have been referring this diagram from the beginning, first chapter, and now we know that for every stage of the data engineering life cycle, there is a separate chapter dedicated. For example, this is one of the stage called as storage, and we are having a separate chapter for the storage phase. So similarly, you can see how many total phases or stages are there in data engineering life cycle. There is a stage called as generations, ingestion, transformation, serving, storage. So we know that these are the total 5 stages, right? Then you have the undercurrents in the form of security, data architecture, orchestration, software engineering, data management, data ops. So regarding storage we are speaking about. Regarding storage we are going to speak about. Now, in storage, we need to understand the raw ingredients for storage. So for that, understanding the raw ingredients, let us look at this diagram which will clearly tell us what is a raw ingredient. You can see here at the lowest layer of this diagram, this block is filled with raw ingredients of storage. So raw ingredients of storage are mentioned as hard disk drive, SSDs, RAM, networking, serialization, compression, CPU. These are the raw ingredients. Now coming to storage abstractions, what are the storage abstractions? Data lakes, data lake houses, data platforms, cloud data warehouse. And coming to storage systems, we have HDFS, cache memory base, RDBMS, object storage, streaming storage. So this diagram we all need to remember, okay? So we need to understand the basic characteristics of all these physical storage systems. We also need to understand what is serialization, compression, caching, because as a data engineer, basically we are dealing with data movement as well as data storage, right? We are playing around with data. We may be generating the data, ingesting the data, transforming the data, storing the data, and while all these movements are also occurring, the storage, consequently that storage also happens, right? So that aspect for that aspect we need to understand or look back to all these raw ingredients of storage. Okay, so in any data architecture, data passes through magnetic storage, SSDs, and memory, because it will be working its way through various processing phases of a data pipeline. What are the processing phases of a data pipeline? That can be ingestion, that can be transformation, that can be serving, etc. Now, many of the topics which we have been learning from our childhood as well as in our first years or maybe in computer organization subjects. So that's why I may be skipping few of them, which I feel you already know it kind of thing, but we'll be referring them also. For example, under raw ingredients of storage, the first one is magnetic disk drive, right? The moment magnetic disk drive, we say, you see these kind of images, right? So when you have your magnetic disk, you have this disk and there is a this rotation will happen and this movement of head will also happen. You all know about this, right? So when I speak about magnetic disk, they have those platters, and those platters are coated with ferromagnetic film, and this ferromagnetic film is magnetized by a read-write head during the write operations to physically encode binary data. Okay, what the read-write head does, it will be detecting the magnetic field and outputs a bit stream during read operation. Okay, now coming to this magnetic disk drive, the moment we say magnetic disk drive, we are speaking about hard disks, and we know that hard disks are cheaper than SSDs, is it not? Okay, but the performance of SSDs is very like far much better than the hard disk or magnetic disks. So this is our typical magnetic disk. There is a head movement, there is a rotation, there is a latency of random access also, right? Now, if you suppose I ask you, do you have a laptop? You will say yes. If I ask you, do you have hard disk? Let us say you say yes, and I may be asking what is the capacity. You may be telling that 1 terabyte, 2 terabyte, something like that. But we also know that the commercially available may be around 20 terabytes also, and newer technologies also added up like HAMR or SMR. Like what is HAMR? Is heat assisted magnetic recording. SMR is shingled magnetic recording. Okay, so but we also know that there is a lot of mechanical movement involved in this hard disk performance. So there is a limitation to hard disk performance because of physics. Say for example, the speed, the disk transfer speed, okay, does not scale in proportion with the disk capacity. It means what? If the disk capacity grows by a factor of, let us say, 4, as mentioned here, the transfer speed increased by only a factor of 2, is it not? Okay, so here he has given an example also. Say for example, there is a 30 terabyte drive, okay, and it takes 20 hours for you to read the entire contents, okay, because there is a limitation of transfer speed which is 300 MB per s. The other limitation can be seek time, the other limitation can be rotational latency, Uh, the other limitation can be IOPS, which stands for input output operations per second. I am anticipating and assuming all this you have learned through, and these are simpler topics. That's why I may be skipping. So the second raw ingredient being mentioned is SSDs, which we all know as solid state devices. So they'll not be using these mechanical things. Movements will not be there. Disk platters will not be there. Instead of that, they'll be using flash memory cells. Okay. So it means SSDs are eliminating the mechanical components like magnetic drives. Uh, that's why in comparison the performance is better. Say for example, data lookup can be in zero point 0.1 milliseconds. uh, Data transfer speeds and IOPS can be scaled up. Okay, so the speeds can be up to many gigabytes per second and tens of thousands of IOPS. Okay, but still SSDs are not the default options for high scale analytic storage. It means what? If you compare hard disk with SSD, you'll say SSD is better, but still they are not a default choice because of the cost. So that's why the alternative is because naturally SSDs are more costly than the HDs. So that's why object storage on hard disks have come as a better option for data lakes, cloud data warehouses, and so on. Then there is random access memory. You know everything about RAMs, right? So, and we know that the most popular among nowadays is DDR5. Is it not? What is DDR5? We know DDR5 stands for double data rate 5. Is it not? It is among the latest of RAMs. The retrieval latency is of 100 nanoseconds, which is 1000 times faster than SSDs. They are expensive than SSDs. When we say RAM, when we say DDR5, we are speaking about system memory. Is it not? Then in raw ingredients we are also discussing, let me just, I had popped up an image of DDR5 also. So this is a DDR5 of Crucial, right? So just as an example image, I am just showing it to you. Okay, let us go back to our content. So under raw ingredients, we discussed what? We discussed hard disk drives, then we discussed solid state devices, then we discussed RAM. Now we are discussing networking also. Why networking also? Because the networking plays a huge role, because everything nowadays is distributed, cloud is there, parallelism is there. So that's why networking, the better the networking, the better the performance, better the strength, better the durability, better the availability and all that. Okay. We also know that new storage standards such as RAID. RAID, all computer science students should at least know the long form of RAID. What is it? Redundant array of inexpensive disks. Redundant array of inexpensive disks. Okay. So what they'll be doing on a single server, they'll be parallelizing, right? Cloud object storage clusters operate here at a much larger scale. Disks are distributed across a network. You have multiple data centers and availability zones. What are availability zones? They are cloud construct which have compute environment with a separate power, water, all the resources. Okay. So you also have multiple zonal storage capabilities also, which will be increasing the availability and durability of the data. So CPU also plays a huge role, right? Because it has to handle all the requests, aggregate the reads, distributing the writes, and so much of the load balancing it has to perform. So networking as well as CPU also are discussed under raw ingredients, along with what? Along with your RAM, along with SSD, along with HDD. Under what topic we are discussing all this? Under raw ingredients of data storage. And this entire thing under what topic we are discussing? Under the topic storage. Okay, this is our chapter storage from the syllabus. So when we come back here, in continuation of that, next point being discussed is serialization, is it not? So first we need to understand what is serialization. Serialization means there are formats, let us say, for standard data exchange. Say for example, you have XML, JSON, CSV files. So they are standard formats of data exchange, right? You have various serialization algorithms for handling types, imposing rules on data structures, exchanging between programming language and CPUs. Okay, so this is what is serialization. So serialization decision will tell how well queries will be performing across the network. CPU overheads, query latency, and many more things. So serialization also is a key thing, along with compression. And what is compression? We all know compression means data is compressed, data is become smaller, less space is taken. Maybe the ratio can be 10 is to 1 as mentioned here. Is it not? That will increase what? That will increase the access speed and everything, scanning speed, everything will be increased, right? Here there is an example given. Let us say you have EC2, okay, EC2 of Amazon, okay, and you have S3. You know what is EC2 as well as S3, right? So this is the speed, let us say 10 gigabits per second. But a 10 is to 1 compression ratio will be increasing this network bandwidth to 100 Gbps. That's what happens with that's what is the benefit of compression. Then you have caching, and you know all the kinds of caches. Maybe you learned in your computer organization like L1 cache, L2 cache, L3 cache, L4 cache, and you also know the purpose of a cache. What is the purpose of a cache? Frequently required instructions or data are kept in those caches, right? There is a cache hierarchy table being mentioned here. And let us ignore the pricing aspect, but you can focus on the fetch latency and the bandwidth. If it is CPU cache, 1 nanoseconds and the bandwidth is 1 TB per second. If it is RAM, it is 0.1 microseconds and 100 Tbps. Similarly, you have data fetch latency and bandwidth of SSDs, hard disk drives, object storage and archival storage, right? Now let us look at the syllabus point again. In the syllabus point, we have storage, raw ingredient of data storage, then you have data storage systems. So what are data storage systems? They are abstractions about raw ingredients, is it not? So let us go back to the diagram so that you will remember that. Where is that diagram? Yeah, this is our diagram. What we covered now, we covered the raw ingredients. What are the raw ingredients? We have seen your hard disk drives, SSDs, RAM, networking, serialization, compression, CPU. Okay, so what are storage systems? They are at an abstraction, one layer above the raw ingredients. What are storage systems being covered? HDFS is there, RDBMS is there, cache memory based storage is there, object storage is there, streaming storage is there, right? So let us move further. We covered serialization, compression, caching is going on. Then coming to data storage systems, your storage can be stored on a single machine, or the storage can be on distributed storage also. This diagram highlights that difference, is it not? One file may be stored on a single machine, the same one file may be stored in a distributed manner also. Okay. Now what a data engineer should be aware of is the consistency paradigm of the distributed system, because now the data engineer is not dealing with a single machine. The data engineer, for a data engineer, the entire ecosystem is distributed, right? Distributed, parallelism, all those aspects will be coming. Now for that, the awareness of consistency paradigm should be there. There is something called as eventual consistency versus strong consistency. This is quite interesting actually. For that you need to recollect your knowledge of DBMS and acid properties, right? Acid, atomic, consistent, isolated, durable and all that. Now here, to understand this consistency paradigm, you need to understand something called as BASE. BASE stands for basically available soft state eventual consistency. Okay, you can think of it as opposite to acid. Okay, and base is the basis for eventual consistency. So what is the long form of base? I'll repeat. The long form of base is basically available soft state eventual consistency. So when I say basically available, it means consistency is not guaranteed. Okay, it will be kind of a best effort basis. Soft state means the transaction state may be fuzzy and we are not certain whether the transaction is committed or uncommitted. Eventual consistency means at some point reading data will return the consistent values. Now coming to the opposite of eventual consistency is strong consistency. So this is very interesting, right? Eventual consistency property. This is the need because of this parallelism and distributed and everything is on a higher side, whether it's storage, whether it is access, you have streaming data, everything is huge. So that's why this. Now coming to file storage, I know what is a file, right? It has properties like definition of file you might have learned in operating system and everywhere. So it has finite length and all that. Okay. Now when I speak about file storage, I should also speak about object storage. Why object storage? Because the moment I start discussing the data science and data engineering, I know that my data is being stored in the form of a object storage, right? When I speak about object, that object can be an image, that object can be a video, that object can be an Excel file, that object can be a CSV file, that object can be anything. And when I speak about object storage, I should be speaking about all the services provided by maybe Apache, maybe Azure, maybe Amazon. So they have all those blob storages, S3s, all those containers, all those capabilities, right? Okay. Then you also have local disk storage. Local disk storage, typical. I have my laptop or my desktop. On that desktop or laptop, I have my hard disk, I have my operating system. Then I have something called as a file system. So that is the base of that. What is the file system there? NTFS, New Technology File System, and XT4. These are the popular ones for Windows and Linux. So what they will be dealing with this file system, they'll be dealing with directory entities, files, metadata. They'll be writing data for easy recovery if there is a crash, if some data loss occurs. So all those aspects. You should also, as a computer science student, remember the long form of NAS. The moment NAS comes, SAN also comes. SAN stands for storage area network, and NAS stands for network attached storage. Just remember that both these terminology, when they come, it means that the storage is huge. The storage is huge, and that storage you need to say, for example, you have Google. It may have huge storage. It may require huge storage requirement. So that it will be sufficing with the help of SANs and NASes. So NAS stands for what? Network attached storage. Okay. So you have dedicated NAS interface hardware. Now, alternative to NAS is SAN, storage area network. Okay. But they provide block level access without the file system abstraction. Then you also have cloud file systems. Which are the famous cloud file systems? EFS. What is EFS? Elastic File System. Given by whom? Amazon Elastic File System. See how we are speaking about different file system. Here which file system we spoke about? NTFS. Then we spoke about which file system? ext4. Now we are speaking about which file system? We are speaking about EFS file system, Amazon Elastic File System, right? So whatever the benefits of cloud Amazon services, say paper storage, pricing, automatic scaling, all those aspects will be helpful. Then we have also learned about blocks in our various subjects, including computer organization. The moment I speak about block, I know that the block size initially was 128, then the block size went to 512. Now the block size is 409596 bytes for the current disk. You should also remember the long form of RAID. What is RAID? Redundant array of inexpensive disks. You can visualize this as a huge rack consisting of many hard disks kind of thing. So it may have, for its support, it may have various parity schemes, encoding schemes for data safety and all. We spoke about SAN, right? Storage area network. Then you also have cloud virtualized block storage. The example for that is EBS, Amazon Elastic Block Storage. This is the default storage for Amazon EC2 virtual machines. Okay. As I said, I'll be skipping most of the part and I'll be just highlighting few of the important parts. You have something called as EBS volumes that you need to remember. So what these EBS volumes will be doing is they will be separating data from the instances. Okay. But they'll be keeping them in the same zone. Why? to support high performance and low latency. Support high performance and low latency. We know about object storage. We spoke about object storage because in data engineering, data is stored using object storage concept only, and the various file types can be text, CSV, JSON. But which are the famous formats? Parquet is one famous format, right? That we always refer. Now, when I speak about object storage, I am speaking about Amazon S3. I am speaking about Azure Blob Storage. I am speaking about Google Cloud Storage. If you remember this regarding Blob, you had done a practical also maybe last week. So the object store uses key value store for immutable data objects, and I think you remember the property of immutable when you discuss about good data architecture principles. Yeah. Let me just scan through. Okay. Then you need to remember this word also called as cache and memory based storage systems. Okay. These we referred during raw ingredients, right? But we referred also what is the purpose of a cache also for quick access and high bandwidth and all that. Okay. Now I need, as a data engineer, I need ultra fast cache systems. Okay. Because I want ultra fast retrieval latency also. The example is memcached. Okay. This is a key value store. It will be caching what? Database query results, API call responses, and so on. Memcached uses simple data structures. It can support either a string or an integer type. Okay. The results will be with low latency. They'll be taking a load of the backend systems. The other example is Redis along with memcache. Also Redis also is a key value store. I should not get confused with key value. The moment key value comes, I should remember the discussion of Hadoop, HDFS and MapReduce, right? There the key value concept had come. Okay. So, but Redis supports some complex data types such as list or sets. It has multiple persistence mechanism, snapshotting and journaling. These points we'll be covering during the physical session which we will be having. Hadoop we have already covered, right? Hadoop, HDFS we have covered in the class. Your name nodes, data nodes and all that. Then you have streaming storages. I'll be just mentioning the example because these are not mentioned in the syllabus, but I want you to look at these technology names. One is Apache Kafka, okay, for streaming. Then you have Amazon Kinesis, Apache Pulsar, Google Cloud PubSub. Then you also have Replay. So these are all for streaming storages. These points you already know: indexing, partitioning and clustering. So I'll be just skipping them. Coming to the next syllabus point, let us see. The next syllabus point is data engineering storage abstractions. Let us look at what is mentioned there. This is it, data engineering storage abstractions, and under data engineering storage abstractions I have data warehouse, data lake house, data platforms and data catalogs. In the class we had covered data warehouse, data lake house. So we'll be just looking at data platforms and data catalogs. Okay. Now most of the vendors, they are styling their products as data platforms. Okay. Sorry for that. These platforms, what they achieve is close integration with object storage for unstructured use cases. Then you also have stream to batch storage architectures. You might have heard about Lambda architecture, which I might have mentioned in the class, right? They are similar to that. The technologies you should remember here is AWS Kinesis Firehose. Okay. Now coming to the last point of Unit 3 is big ideas and trends in storage. Coming to big ideas and trends in storage, one of the big ideas is data catalog. Okay. Sorry, let me switch off. Okay. So what is a data catalog? It's a centralized metadata store for the entire data across an organization. It will be running across operational and analytics data stores. It integrates data lineage and presentation of data relationships and allows user editing of data descriptions. It is kind of a central place where all the people can view the data, the queries, the data storage. Okay. So what is the role of a data engineer in data catalog? He'll be setting and maintaining the various data integrations, data pipelines, storage systems that will be integrating with the data catalog and the integrity of the data catalog itself. Okay. This I'll be skipping. The other concept is data sharing. Okay. So when I speak about data sharing, I'm speaking about a common ecosystem like a cloud where you have multiple tenants sharing the space, sharing the data and all that. So this I'll be skipping. And one aspect you should always remember is we are moving away from Hadoop now, because now there is a discussion on something called as separation of compute from storage, right? So initially what happened was storage and compute were kept nearby so that the speed and everything could be achieved faster. But now with the newer requirements, the data engineers ecosystem needs this compute and storage separation. Okay. So with this I'll be stopping today's discussion, and with this I declare unit 3 to be finished. And thank you for attending today's session. Any